Hey guys, welcome back to another wonderful lab that we've done. I just want to go over this lab, give you guys some feedback. First off, I'd like you to, after you finish the lab, give your Chromebook to a friend so they can look at your lab, and then they're going to give me the feedback on how they think you did. What we call in science, we call this peer review. Any scientific paper that gets written goes into somewhere to get published, and those publishers actually send it out to other scientists to see if the science was good, because the publishers, or the people that actually send the papers out to the public, don't know if the science is good, so they send it to other scientists to see what they think. So you guys are my other scientists, so you guys are going to pick your peer reviewers. So pass off your Chromebook and let them take a look at your lab. As you go through, if you see one of the boxes that's wrong, go ahead and keep track of that in a comment. You can even do a comment to yourself. So you can highlight that box and then just add a comment of, points off, and then maybe tell them why you're going to get them points off. And so you can click that comment button up to the side and then add a little comment as to why they lost the point, what you thought the right answer was, or what you didn't like about their answer. All right, so the force lab, the purpose of the lab was obviously to look at the difference between mass and weight, and you could have done weight or mass there. Generally, what we're looking at is as the mass increases, we think the weight of the object will increase. So let's take a look at the lab and see how we did. Now, I can't comment on what everyone's data table should look like. I can tell you if the numbers seem reasonable, but you guys, one of the first things you could check to see if people were able to do is the conversion between mass in grams and kilograms. So if an object was 1 gram, we're going to move that decimal place 3 spots to the left, and so the mass in kilograms would be 0.001 kilograms. In the same sense, if it was 1,000 grams, move the decimal place 3 spots, it would be 1 kilogram. So first thing I would check on this data table is to make sure that the conversion between mass and kilograms is correct. In that same sense, when you're looking down at this part of the lab, this orange column should be that orange column up above, and the blue column should be the blue column up above. So those things should be fairly straightforward to check for your friends. Now, as far as what this data table should look like, if the force was 1 Newton, it turns out the mass in kilograms should have actually been around 0.1 kilograms. And so what your graph should look like is, let's see if I can get this to do what I want it to do. Your graph should have looked actually something closer to this. It should have been a fairly straight line that actually ended at 0, 0. And the ratio between these ones should be, if you took this first column and divided by the second, you should get a number close to 10, actually. In particular, the best answer you would actually get if you guys had great numbers would be, if you took the first column divided by the second, you would actually get 9.8. Would be an exceptionally good data set. So the number should be kind of close to 10. And so this is about the line that we are looking for in this lab. So as the mass grows up, the force in newtons goes up. And that makes sense. If you have more mass, you should have more weight on Earth. For your first answer right here, what type of force do you measure in this lab with the spring scale? Spring scales, of course, measure forces. And so we were measuring a force. And in this lab, we measured the force of weight, the weight on the object due to gravity. That would be the best answer. Make sure there's a turnaround. One-word answers like weight would not be appropriate and should not receive full credit. In this lab, if many of you guys didn't actually do a rock, but if you did do a rock or some odd-shaped object, it is important for any object that was oddly shaped that you couldn't get onto the hook, that you may have had to use like a string or a rubber band or maybe even a bucket to hold that object. And when you're finding the mass or the weight of it, make sure that you're including or thinking about the fact that you also found the mass of the string and the weight of the string that is included in that, or the weight of the rubber band and the weight of and the mass of the rubber band. So anytime you're doing a measurement, be conscious. Like same thing when we were measuring water or finding the mass of the water. You need to make sure that you're subtracting that container from your math. So anytime you're using a method of suspending something or hanging something off, make sure that you think about whether or not you need to subtract anything because you didn't actually want to find the additional weight or mass of the string or the bucket or some other irregularly shaped object when you're doing a lab. So always a good thing to think about when you're making your measurements. And that's the purpose of that question right there. Okay, observe any similarities or differences in the readings from a 5 Newton scale and the 20 Newton scale on the same object. Are the values the same, and should they be the same? If you use any of the scales, when should you use each of them? And of course, you want to use the scale that's closest to the number. And so we had 2.5s, we had 5s, 10s, I think there's a couple 20s in there, 30s and 50s mixed in there. And clearly, you want to use the one that's closest to that measurement. So for a light object, they should actually read the same. It's just going to be a lot easier to get a good and accurate measurement when you use this lighter spring or the smaller spring. So for small objects, the 5 Newton springometer or Newtonometer would be best. For the larger objects, clearly you couldn't use the 5 Newton one because it would go off the scale and it would actually break it as well. So make sure that you are using the scale closest to the actual weight of the object for accuracy and to keep the instruments working well. The most accurate scale is the one where the weight is in the middle of the scale ranges. And so if you had to use, say, that 5 Newton scale, it would be most accurate when the weight that you put on, the force that you put on is 2.5 newtons. And so these spring scales are most accurate when the scale is sitting right in the middle of the measurement. They're not very good at the beginning, they're not very good at the end, because the springs just dynamically just work that way. And so you want to use them, try to get them sitting just about the middle of the scale. So for our 30 Newton scale, they're going to be most accurate at 15 newtons. What would happen if your measurements, if you set your spring scale to 0, if it was not set to that when you started the lab? And in that case, your accuracy is going to be off. Let's take, for example, if it was off by 0.2 newtons, like in some of those, about 2 lines off. What that would mean is that all your measurements for the entire lab are going to be off by 0.2 newtons. And so that making sure that your instruments are accurate in the beginning of the lab is always important, else your graph might be off by that much the entire time. And you might see that in your graph. If it doesn't actually go through the origin, through the 0.00 on the graph, it might be due to the fact that you did not zero your spring scale or your triple beam balance. Where do you often see spring scales outside of school, and what are they used for? We often see them in grocery stores, and especially in the bulk food sections or the produce section where you're going to buy food by weight. Often we buy them in boxes or it's already measured out, but when you get to pick it out and then buy it, you often need a scale there to find out what is the weight that you are purchasing. And so you'll see them there. And of course, in the checkout lines, the scanners that they have, those scanners are also measuring the weight of it. That's why they can put the bananas or whatever on that little scanner, and it has a spring in it to tell it how much force is being applied to it, so they can tell you how many pounds of bananas you brought. So grocery stores are a great example of where you guys are going to see spring scales outside of school. If you weighed your shoe with 2 spring scales, one side by side, sorry about the picture, then what do you think would happen to each, and how would the measurement compare to one scale? So let's assume that you had a shoe and you put it on there with one scale, and it had force due to gravity of 10 newtons. If you then hooked a second spring scale on it, the force is now going to get divided in half, and half's going to go up one spring scale and half's going to go up the other. And so the total force on is still going to be 10 newtons, but each one's going to be taking 5 newtons. So each spring scale would read 5 newtons if you had 2 for the total of 10 newtons. So it's going to get divided. Okay, so in this last question, did you notice the relationship between mass and weight, and how are mass or weight the same, and how are mass and weight different? So in the lab, we clearly saw that they are related. In your graph, as one increases, the other increases. That's your line that kind of goes up to the top right corner of a graph. That shows that they're related. As one increase, the other one increase. However, we did find that they are different. We didn't get the same numbers. It's not like for 1 Newton, it was 1 gram. So they're not directly related. They're not exactly the same. The other, of course, and really important thing is that mass and weight are not the same. Mass, of course, is the amount of matter that's in the object. And I hope never to be massless. That means that I'd have 0 atoms, and there wouldn't be anything of me. I wouldn't have any carbon or life. I don't want to be dead. I don't want to be dead. So I don't want to be massless. However, weight is the force due to gravity on this planet. And that's what we found. We found only the gravity on this planet. And so someday I do hope to be weightless. So I'd love to get outside of Earth's gravitational field, or at least get into a free fall situation in where I could have mass, still be alive, be me, but be weightless, not feel that force of gravity. And so make sure that you can distinguish between those two things. In this lab, what you guys actually did calculate is the force of gravity on Earth. If we did this experiment on a different planet or on the moon, we would get a different curve on a different line on our graph. And so that ratio of the 1 to 10 that we saw here, or 1 to 9.8 to be more accurate, that is actually the force of gravity, the pull of gravity on Earth. And so I did talk about that, especially if you're in advanced math, and I'll personally go over that with you guys there if need be. All right, thank you guys. Good job on the lab, and I will talk to you in class. Oh, sorry. Before we go, make sure that you send a private comment in Classroom as to what this student, your peer-reviewed student, deserves on this grade one. Not the person that actually wrote the lab, but the person that did the grading on it. The lab itself has just about 15 questions on it, and so you can make this your little comment. Make sure it's a private comment back to me, not inside the lab, but your comment should be a score of out of 15. So when you go back to the Google Classroom and click on the private comment to Mr. Straub, go ahead, put the first thing down there as the score of 1 or whatever score you think they deserve out of 15. So if they got a perfect score, 15 out of 15. Thanks, guys. Have a great day.